So you can see the slides here if you want to.
Thank you. Yes.
Okay.
Yeah.
All right. Second speaker in this section is Robert Andrews, who will tell us about Hilbert Nullstellensatz and the counting error.
All right. Thanks, Srikanth. So thanks to the organizers for putting together what's going to be, I think, a very exciting workshop. So I want to tell you about some new complexity results on this problem called Hilbert's Nullstellensatz. This is joint work with Abhibhav Garg and with Éric Schost. We did this all at Waterloo. I'm going to be moving to Simon Fraser University in the fall. Abhibhav recently graduated. He'll be starting his postdoc in Toronto very soon. And Éric, well, he remains faculty at Waterloo. So let's get started. So this is what we're going to talk about today is the problem of solving systems of polynomial equations. And really, we're going to look at the decision version of this problem. So your input is going to be a system of polynomial equations. I guess you can't quite see the laser. I'll give you m polynomials, f1 through fm. They all have integer coefficients, and your job is to decide if this system of equations, where all the polynomials equal 0, you need to decide if this has a solution. And of course, to make this more precise, I need to explain a couple of the words on this slide. I need to explain what I mean by you're given the polynomials, what I mean by decide, and of course, what I mean by a solution. So when I say you're given these polynomials, I mean you're given them as a list of monomials and their coefficients, along with all the 0 coefficients. This is sometimes called the dense representation of these polynomials. When I say decide, your job is to design a Turing machine. So we're working in the bit complexity model. You don't get arbitrary complex numbers for free. And finally, when I say a solution, there's some ring R where we care about finding these solutions. And where we're looking for the solutions really changes the complexity of this problem. If I ask you, say, for integer solutions, well, this is an undecidable problem. But instead, if I ask you for complex solutions, then this problem becomes decidable. And so often in this talk, we'll look for solutions in the complex numbers or more generally in an algebraically closed field. So, why Hilbert's Nullstellensatz? Well, this gives us a decision criterion for this problem over the complex numbers. So the Nullstellensatz is this beautiful mathematical theorem due to Hilbert that says if I have this system of polynomial equations, there are no complex solutions exactly when there are auxiliary polynomials, g1 through gm, so that when I take f1 times g1, f2 times g2, and so on, and I sum all of these up, I get the constant polynomial one, right? This is a certificate for non-solvability of polynomial equations. And you can use this certificate to design decision procedures for this problem. Now, somewhat confusingly, because the Nullstellensatz is so useful in solving polynomial equations, we also call the decision problem the Hilbert's Nullstellensatz. So when I talk about the complexity of the Nullstellensatz, what I really mean is the complexity of this decision problem here. I give you m polynomials as input. They all have integer coefficients, so a Turing machine can read them. And the yes instances are exactly those systems of equations that are solvable over the complex numbers. So this is the decision problem we'll really be interested in. Of course, there's nothing special about the complex numbers here other than it's an algebraically closed field. So you could look at this problem over other fields. And one other version of this problem I'll mention is the decision version over the algebraic closure of the finite field with p elements. That made it worse. So in this other variant, I'll give you m polynomials, but now they have coefficients in fp, the finite field of p elements. And I want the yes instances to be those systems of equations that are solvable in the algebraic closure. Okay, so what do we know about the complexity of this problem? So I want to fill out this chart. The columns are labeled by, well, I'm going to tell you some lower bounds, some upper bounds, and some conditional upper bounds for these problems. And a priori, the complexity can depend on the field we're looking at. So we'll talk about characteristic 0 with the complex numbers, and we'll talk about positive characteristic, which the model for that will be the algebraic closure of FP. So it's easy to see these problems are both NP hard. You can just reduce satisfiability to them. Now, on the other hand, that's kind of the best lower bound we have. In terms of upper bounds, you can solve both of these problems in P space, in polynomial space. And then you can ask, well, this is kind of a big gap between the complexities of these problems, right? We have an NP hardness lower bound, we have a P space upper bound. What should the right answer be? And conditionally, we know, at least in the characteristic 0 setting, what the answer probably should be. So Pascal Poisson showed that if you assume the generalized Riemann hypothesis and you assume some kind of de-randomization assumption, you can solve the Nullstellensatz over the complex numbers in NP. So at least in the complex case, this is really an NP-complete problem. We just need to prove that it's NP-complete. And here, proving the NP upper bound is the hard part. Unfortunately, in the FP bar case, we don't have any stronger conditional upper bound. So even if I give you some strong mathematical or complexity theoretic assumptions, we don't have a stronger upper bound than polynomial space. And what I want to tell you about in this work is we were able to improve the upper bound unconditionally, both over the complex numbers and in the FP bar setting, from polynomial space to this class CH called the counting hierarchy. So this is a somewhat less familiar class, at least to me. I mean, I didn't really know much about the counting hierarchy before starting this work. So before I tell you what our results are, I want to tell you what the counting hierarchy is, so you have a better chance at putting this into context and understanding what this result actually means. And so to do that, I want to remind you, of an alternate characterization of polynomial space in terms of quantifiers. So we're all familiar with the fact that NP is really like a polynomial time Turing machine where I give you one existential quantifier. And similarly, the polynomial time hierarchy, this is like polynomial time machines with a bounded number of existential and universal quantifiers. And you can also characterize polynomial space as a polynomial time machine that has unbounded alternation between existential and universal quantifiers. And if you've never seen this before, this is just a precise way of saying this, that a language can be decided in polynomial space if there's a polynomial time machine M, so that you can write the language in this form. It's strings X, so that there exists a string Y1 for all Y2, there exists Y3, and so on, so that three criteria hold. The machine accepts. The length of each of these witnesses Y is polynomially bounded, and there are polynomially many witnesses. Right? So polynomial space is really polynomial time with unbounded alternation between exists and for all quantifiers. And the counting hierarchy, well, it's easy to define in terms of quantifiers. So this class CKP, this is the kth level of the counting hierarchy. This is what you get when you take a polynomial time machine and allow yourself k nested majority quantifiers. So instead of exists a string y or for all strings y, I say for a majority of strings y, at least half of them. And then when you take the union of these classes over all natural numbers k, this is what the counting hierarchy is. So this gives you a constant number of majority quantifiers. It's easy to see that the counting hierarchy sits somewhere between the polynomial time hierarchy and PSPACE. And in fact, the counting hierarchy is very strong. So Toda's theorem tells you that the entire polynomial time hierarchy lives in this class p to the sharp p, which really is just in the second level of the counting hierarchy. So the counting hierarchy is a quite strong class. Another way to think of it is these are all the problems that if you could compute the permanent in polynomial time, this is exactly the set of decision problems you can solve in polynomial time. Just in the same way that the polynomial time hierarchy is the class of decision problems you could solve efficiently if satisfiability had an efficient algorithm. Okay, so this is nested majority quantifiers. That's what the counting hierarchy is. So now let me tell you what our results are. So of course, our first main result is that you can solve this Nullstellensatz problem over the complex numbers in the counting hierarchy. So instead of alternate, yes?
Yeah, just a quick question. How do you represent numbers in complex?
Right. How do you present numbers in the complex in the computational problem H and C?
Right, so all the inputs are integer coefficient polynomials, so I just write them down in binary. And it's a Turing machine, so it's only ever going to do bit operations. There's no complex numbers magic going on.
So the solutions are complex, but the input is integer.
Right, so the question for those of you online, the solutions are complex, but the coefficients are integers, yes. And we'll never actually write down the solutions. We're just deciding if they exist. Okay, so we can show that the Nullstellensatz is in the counting hierarchy over the complex numbers. We can show that it's also in the counting hierarchy in the FP bar scenario. So remember, this is the algebraic closure of the finite field of P elements. We can solve this in the counting hierarchy. And the most general version of this theorem we have is we can show that the Nullstellensatz is in the counting hierarchy over the algebraic closure of a field F that looks like a rational function field over a finite extension of the rational numbers or a finite field. So this is the most general version of the result that we have. Let me tell you some corollaries of this. So there are two sort of easy algorithmic corollaries that we can get for this. One is for the radical ideal membership problem. So here, we're given polynomials f1 through fn and an extra polynomial h. And we can decide in the counting hierarchy if there's a natural number k and additional polynomials g1 through gm, so that h to the k is the sum of fi times gi. And for those of you algebraically minded, this is really asking, does h lie in the radical of the ideal generated by the f's? So this is sometimes what's called the strong Nullstellensatz, where deciding solvability is the weak Nullstellensatz. So we can solve this in the counting hierarchy. And then another thing we can do is, if I give you some algebraic variety given by its equations, and I give you some number r, you can decide in the counting hierarchy if this variety is r-dimensional. Right? So you can compute dimensions of algebraic varieties. And you might think that this is sort of a bit of a proxy for how big is the solution set to your polynomial equations. So this is our first batch of results. We have a second batch of results about counting complexity. So here, I want to show you one more problem. So this is the counting version of the Nullstellensatz, sharp HNC. So again, we're given m polynomials with integer coefficients, and I want you to count the number of complex solutions. Of course, this number might be infinite, so if it's infinite, you better report that. But you can decide if it's infinite. This is the same as checking if the variety is positive dimensional, which we can do from the previous slide. Okay, so I want you to count the number of solutions, and you can similarly ask about this problem where you count solutions in the algebraic closure of a finite field. And we show that both of these problems can be solved in this class called fp to the ch. So what is fp? Fp is function problems that are solvable in polynomial time. And the exponent ch just means you get an oracle to the counting hierarchy. So you should think of this is a function that's sort of computable in the counting hierarchy. Just the formal precise statement is this. But really, one way you can think of this is if I give you this system of equations and I ask you for the value of the ith bit of the count, you can decide the value of the ith bit of the count in the counting hierarchy. And why I think this is interesting is this sharp HN problem. This is actually a sharp p-hard problem. Right? Counting solutions to polynomial equations, that captures counting solutions to satisfiable or unsatisfiable Boolean formulas. And this is a sharp p-hard problem. And the counting hierarchy is kind of in the neighborhood of sharp p. And the fact that we're getting this counting hierarchy upper bound, we're kind of getting the right answer for the counting complexity. But I think more importantly, all the techniques we use for the counting problem are based on the techniques we use for the decision problem. So this kind of suggests that everything we're doing to solve the decision problem, you'd like to prove that you can solve the decision problem in PH, the polynomial time hierarchy, but we can't. Right? These techniques they're solving a stronger problem, a harder problem, excuse me. So that's everything I want to say about the results. Yeah?
Do we know anything about how high is the level?
How high is the level? I was hoping you didn't ask that.
I didn't ask.
It says you didn't ask. So I did not estimate, I didn't compute the level ahead of time, but I would say it's at least a 3 or 4 digit number. So let's talk about that at the end. Yeah, it's definitely not the right number. Any other questions about the results? Yeah, Amir.
Distinct roots or multiplicities as well?
Oh, that's a great question. So the question was, do we count distinct roots or are we counting with multiplicity? Distinct roots. Otherwise, Bezout just tells you the number. Yeah. So here we're really counting distinct solutions, ignoring any multiplicities. Yeah. Any other questions about the results? Yeah, Ilya.
Specifically about that, so when you go from Z, usually your solution is going to be some kind of a number field, not necessarily in C. So do you actually care about this, or you want just C in general?
Okay, so do I care about C in general, or do I care about some number field? No, I mean...
Okay, change the problem. Instead of calling NHC, call it NHQ, whatever. So
yeah, Q bar.
Does it change the problem?
No. As long as you take whatever domain you're starting with, you take its field of fractions, you take its algebraic closure. That's it. Okay. So now I want to tell you a little bit about the algorithm and how we do this. I won't give you many details, but I want to just give you a picture. So how would you decide the Nullstellensatz? Right? Well, we have this theorem, the Nullstellensatz, that tells us if we want to decide if these polynomial equations have a solution, we might as well try solving for these g's so that the sum of fi times gi is 1. And the benefit of doing this is now this becomes a problem in linear algebra. This system of equations is really linear in the coefficients of g1 through gm. And so if we knew bounds on the degrees of these g's, if they existed, we could make this a finite system of linear equations. And we have these kinds of bounds. These are theorems called effective Nullstellensatz. And the first theorem that really has the kind of bounds that we want is due to Brownwell. It says if you're looking at this system of equations f1 through fm, and all the polynomials f have degree bounded by d, then you can find these g's of exponential degree. The precise exponential function doesn't quite matter, but you get some exponential bound here. Okay, so we're trying to solve this system of linear equations. We know the g's have exponential degree. And this means that really we get a linear system of exponential size. When you write down exactly how many equations and unknowns there are, there's exponentially many of them. And we can solve systems of linear equations in polylogarithmic space. We have very space-efficient algorithms for linear algebra. And so the punchline of this is you can solve this exponentially large system of linear equations in polynomial space.
The same question
Yeah.
arises. The same question. How do you know the coefficients themselves when you need to solve a system of equations?
Mm-hmm.
Oh, I see. The equations are in integers also.
Yes, so all the equations we manipulate have integer or rational coefficients.
Right. Thank you.
Okay, great.
Question?
Yeah.
Is this really exponentially many equations? Is that your input size, I thought was like d to the n or something?
Well, okay, so it depends on exactly what parameter regime. For example, if the f's were quadratics, then you have like n squared input size, roughly. But here you do have like a 2 to the n bound on the degree. So sort of in that really bad case. But you're right, as the degree of the f's grows, this is more like polynomial time. Okay, so we saw that we can use linear algebra to solve this, and the big question is, can we beat linear algebra? Can we do better? Could we solve these really large linear systems in the counting hierarchy? And the answer is probably not. There's a result by Grenet, Coiron, and Poitier that shows that this sort of succinct linear algebra solving these very large systems is really PSPACE complete. So we're not going to do better just by improving linear algebra. Really what we're going to try and do is we're going to try and exploit the specific structure of the linear systems that appear in the Nullstellensatz, right? These are not general linear systems, they have structure. And for the rest of this talk, I want to focus on one case, which is deciding if a system of n homogeneous polynomials in n variables has a non-zero solution. Homogeneous polynomials are always 0 at 0, so I want a non-zero solution. If this means something to you, we're looking for a solution in projective space. Sorry, I went too fast. Right, so n homogeneous polynomials, n variables, non-zero solution. Okay, so let's do a warm-up. Let's look at the case of two variables. So we have two polynomials, f and g. And if you write down the Nullstellensatz, you use the degree bounds, you'll see that this system has a non-zero solution if and only if this determinant is 0. Okay, so this is a big determinant. It's like a 2D by 2D determinant. But the point is it's very structured. You have the coefficients of f and g appearing in these nice parallelograms. This thing has a name. It's called the resultant of f and g. This is a well-studied quantity by mathematicians. So really deciding the Nullstellensatz in this case is about computing the resultant better. And we can compute this using any algorithm for the determinant, but can you do better? And it turns out you can. So a couple of years ago, Avi and I looked at this problem, and we showed that you can compute these resultants using arithmetic circuits of polynomial size and constant depth. You would get polylogarithmic depth for the determinant. And a corollary, which I didn't realize until recently, Avi, maybe you realize this, is this says that the resultant is in this class TC0. Okay? And these are the Boolean functions computable by threshold circuits of polynomial size and constant depth. And the way you prove this is easy. Iterated addition and iterated multiplication are in TC0, so you just simulate the arithmetic circuit in TC0. And why am I telling you about this? Well, TC0 is kind of like a scaled down version of the counting hierarchy. You have a constant depth circuit. Every gate is majorities. That should sort of feel similar to this constant number of nested majority quantifiers. So this is at least some indication you can do better. Okay, but this was just the warm-up for n equals 2. I told you about the resultant. Now I need to tell you about the resultant. So there's this really amazing result by Macaulay from the early 20th century that finds this amazing polynomial called the resultant. Okay, so it's going to be parameterized by two numbers, n and d. And there's this magical polynomial that just solves our problem for us. Okay, so if this n-variate degree d homogeneous system has a non-zero solution, then the resultant will tell us that. Okay, the resultant eats all the coefficients of this system, and it spits out a number. And if that number is 0, the system has a solution. If the resultant is non-zero, there is no solution. Okay, so the way I'm writing this here, it looks like this is maybe the resultant composed with these polynomials. It's really eating their coefficient vectors as the input. Okay? So that's one property that the resultant has. It tells us if a system is satisfiable. And then just to, there are many polynomials with this property, in fact, so we have to normalize. So the resultant on the system x1 to the d through xn to the d, it's 1. This is like saying the determinant of the identity matrix is 1. And then as a formal polynomial, the resultant must be irreducible. Now, this resultant is kind of a complicated object, but I claim you've seen it before. So in the case of two polynomials of degree d, you all know this resultant. It's this determinant of these two parallelograms I showed you earlier. And if you have n polynomials that are all linear, well, this is just the determinant of their coefficient vectors. So really, the resultant is somehow a generalization at one point of this bivariate resultant you might have seen before in an algebra class, and on the other hand of this determinant. So we need to compute this. And how can we compute it? I'll just tell you that you can express the resultant as a quotient of two exponentially large determinants. And this means you can compute it in PSPACE. And the main lemma that we show in our work is that you can in fact compute this resultant using uniform arithmetic circuits of constant depth and exponential size. Taking these arithmetic circuits, you can simulate them by threshold circuits of constant depth and comparable size. And this is exactly the sort of thing that the counting hierarchy lets you evaluate. Okay, now I'm skipping a lot here. The real, the main sort of insight in this work is about computing these resultants using constant depth arithmetic circuits. The rest of this is sort of machinery that was known in some form or another in prior work. So let me just tell you how you might compute the resultant in constant depth. I haven't even told you what it is yet. Oh, I can use this one as well. Perfect. Okay. So there's this amazing formula called the Poisson formula. Okay, and this is what we're going to use to compute this. So I have these n-variate degree d homogeneous polynomials. I need one bit of notation. So from fi, I get fi bar by setting the last variable to be 0. And from fi, I get lowercase fi by setting the last variable to be 1. And what the Poisson formula says is if the resultant of f1 bar through fn minus 1 bar is not 0, then the resultant of n polynomials factors into two terms. The first term is a recursive term with n minus 1 polynomials. And then the second one is something surprising. It's you look at all roots of this system of n minus 1 polynomials, take each root alpha, evaluate the last polynomial at alpha, maybe with some appropriate multiplicity, and you take the product of all these evaluations. Okay, now if I gave you these solutions alpha, you could implement this term very efficiently in low depth. This is just a product of polynomial evaluations. But of course, it's not at all clear how you would get these. That seems like, getting these alphas is really like solving polynomial equations. That's what we're trying to do. So how are we going to compute the resultant? Well, first you expand this Poisson formula recursively, so you get many of these different evaluation product terms. And this is where I'm going to wave my hands and say you use an explicit version of the multivariate implicit function theorem. You go to the right book, you look at the right formula, and it's there. I think this is inspired by recent work by Bhattacharjee, Kumar, Rai, Ramanathan, Saptarishi, and Saraf on factoring constant depth circuits in constant depth. And I think Mrinal and maybe Shantanu will speak about the univariate version of this more later in the workshop. There's not any sort of great intuition to be gained from me flashing a formula here, but I'd be happy to talk more about it offline. So I'm starting to run out of time. Let me just tell you what this talk didn't cover. There's more in the paper. So I didn't speak at all about the uniformity of these circuit constructions. This is tedious, but it's important for the counting hierarchy bound. There's not too much insight to be gained from this. One thing that's very interesting is this generalized characteristic polynomial of Canny. I only spoke about solving systems of equations where the number of equations and the number of variables was the same. And I was only looking for non-zero projective solutions. To really solve the whole HN problem, you can get this by computing resultants, but it needs more work. It's more complicated, but this was already worked out back in the 80s and 90s. How do we solve the counting version? Well, here you need TC0 circuits, so constant depth threshold circuits, to compute things like polynomial GCD and square-free factorization, which thankfully was already done for us in prior work. So that was not so bad. And then I only spoke about characteristic 0. How do you handle characteristic P? Well, you have a Turing machine. And if I give you numbers, elements of FP, you can lift them to the integers and think of them as integers between 0 and p minus 1. Now, you can, of course, do some computation in the integer case and then reduce back down modulo p. And the important thing is that the modulo, the resultant over fp bar is really the same as the resultant over c, where I reduce all the coefficients mod p. The resultant has integer coefficients, so this makes sense. Okay, so open problems. Ramprasad asked about what level of the counting hierarchy. It's probably at least 1,000. Can you do better? Please. That would be really great. More ambitiously, could you show that over the complex numbers, could you put this in the polynomial time hierarchy unconditionally? And finally, this sort of idea of solving very large linear systems, this is prevalent throughout computational algebraic geometry. Take your favorite problem that's in PSPACE. Can you put it in the counting hierarchy? Here are some examples. If you want to know more, here's a QR code for the paper. Thanks so much for your time.
Okay, great. Thanks so much. Questions?
Thank you, Andrew. I think it's a very exciting result. Did you already think about the end corresponding question over the reals? So feasibility of a system of polynomial equations inequalities is called existence theory over the reals, and it's very popular in computational geometry. And I think that it could be as well in the counting hierarchy.
Right.
So did you think about it?
I've thought about it. I'm stuck. So I'd love to talk more about it.
Yeah. I think it's related.
It's
the sub-resultants.
yes.
The result with RD, if can be extended somewhere to sub-resultants, then you have this Sturm sequences.
Right.
Like the key ingredient to all these.
Yeah, so there are some barriers to using Sturm sequences, but I don't think it's entirely hopeless. But the existential theory of the reals is, it's more complicated, but it's very related to resultants and sub-resultants.
I think maybe the first problem is just look univariate.
Yes.
You have two polynomials like f and g. You want to count the number of real zeros in an interval?
Yes, even just one polynomial, even detecting if it has a real zero.
But
I don't know how to...
bounded depths and polynomial size.
Yeah. So doing that, I think, is a fantastic problem.
Very exacting.
Yeah, absolutely. Let's talk more.
Yes, thank you.
Great, thanks. Other questions?
Yeah, thank you so much, Robert.
Yeah.
I'm curious, do you think this is implementable and possibly as a practical alternative to arithmetic-based computations?
That's a great question. I probably not, but I don't know. Grammar bases actually work. I don't know if I could get this running in small. I don't know, but I feel like maybe not.
Yeah, okay, I think that's a fair answer, but arithmetic bases don't always work. Sometimes it just takes forever to compute.
Right.
And, this might also take forever to compute, but it might be smaller.
Yeah, that's true. Yeah, if someone wants to, think about implementing this, that would be great. Yeah.
Okay, can I ask